In this video, we are going to discuss limiting reactants. In a particular reaction, when we mix reactants, we seldom have the exact stoichiometry ratio from the balanced chemical reactions that will be mixed together to form my product, which means that both of my reactants are going to be used up and I have nothing left over. Most likely what's going to happen is that one of the reactants is in the lesser amount and is going to be used up first. That reactant is called a limiting reactant. It's called limiting because it doesn't allow me to make any more product because it runs out faster. So it limits the amount of product that I can make. The other reactant, however, it's in excess, and we call that excess reactant because some of it is going to be left over. It's not going to completely run out, so it's in excess and is present in greater quantities than necessary. When we calculate these types of problems, and so in these types of problems, we have to first determine which is the limiting reactant. You will recognize these problems when you will have amounts in grams or in moles given for both reactants. If it's only one reactant that's given to you, then that implies that the other one will be in excess. But if you have amounts, whether in grams or in moles, it doesn't matter, but amounts for both reactants, that is a sign to you, it's an indication that you have a limiting reactant problem, and the first thing you need to do is determine which one is going to run out faster. How we do that is we take each amount for each product and we calculate, the amount of each reactant, and we calculate how much product is that going to give me. Once I calculate that, the one that results in the smallest amount of product made, that is the one that's going to run out faster, that reactant. Let's take a look at a problem. If you mix 20 grams of CO with 10 grams of H2, how much methanol, CH3OH, will you make? Once again, here's an amount for one of my reactants, and here's an amount for my other reactant. I have amounts given for both reactants, which means that one of them is going to run out faster. Note that you cannot tell directly by just looking at the mass in grams which one's going to run out faster. It's not that easy. But what we can do to determine which is going to run out, we have to figure out if I used up all of this 20 grams of CO, how much product am I going to make? And then in a separate calculation, if I use up all of the 10 grams of hydrogen, how much methanol am I going to make? Let's take a look. Here's my reactant, and here's the first calculation. I have, so mass of my reactant, 1. I cannot go directly to mass of product. I have to go mass to moles, to moles, to mass again. To do the conversion from mass of my reactant to moles of my reactant, I use the molar mass of CO. So I take 20 grams and I figure out the molar mass of CO, and I divide by that because I'm going from grams to moles. I divide by the molar mass, which is 28.01 grams per mole in this case. That gives me 0.7140 moles of CO. Now that I have moles of CO, I can go to my balanced chemical reaction and figure out how many moles of CH3OH are made for every mole of CO. What are the coefficients here telling me? Well, they're telling me that I make 1 mole of CH3OH for every 1 mole of CO. It's a 1-to-1 ratio. So here's my ratio here. I multiply my proportion, if you will. I multiply 0.714 moles of CO by this conversion factor. My moles of CO will go on top because I want them to disappear. moles of CH3OH on top, moles of CO at the bottom, moles of CH3OH on top because that's what I want to end up with. Then this becomes an easy 0.7140 times 1 divided by 1, same amount of moles of methanol. Now that I have moles of methanol, I can convert to grams using the molar mass of methanol, which is 32.04 grams per mole. Moles will cancel. I multiply 0.7140 by 32.04 divided by 1, giving me 22.9 grams of CH3OH. If I used up all of those 20 grams of CO, I would be making 22.9 grams of CH3OH. Now, we repeat the same thing, but with the amount that we are given for the second reactant, which is hydrogen. I take that amount, convert that to moles by using the molar mass of hydrogen, so 10 grams divided by 2.016 gram per mole, gives me 4.960 moles of H2. Now, what is my relationship, molar relationship from the reaction between methanol and hydrogen? Well, I have 1 mole of CH3OH that is made for every 2 moles of H2. My moles of H2 are going to cancel, leaving me with moles of CH3OH on top. 4.960 times 1 divided by 2 gives me 2.480 moles of CH3OH. Once I have moles of CH3OH, I can convert to grams of CH3OH using the molar mass of CH3OH, just like I did here, because it's the same molecule. I use the same molar mass. 2.480 times 32.04 divided by 1, I get 79.5 grams of CH3OH. So if all of that 10 grams of hydrogen was used up, so if hydrogen were the limiting reactant and all of it ran out, I would get this much product, 79.5 grams. If carbon monoxide were the limiting reactant and all 20 grams were used up, I would make 22.9 grams of CH3OH. Since this amount is the smallest of the two, that means that carbon monoxide is my limiting reactant. And I cannot make any more product than what CO dictates, what it allows me to make. So I will only make 22.9 grams of CH3OH, use up all CO, and have a little bit of H2 left after the reaction is done. Let's look at another example problem. Ammonia is produced by the reaction of nitrogen and hydrogen according to this reaction here, and it is balanced already. Determine the limiting reactant and calculate the mass of ammonia produced when 35 grams of nitrogen react with 12.5 grams of hydrogen. Which is the excess reactant, and how much of it will be left over when the reaction is complete. So the first part is just like the problem that we got done doing. The next bit, so the next part of this problem is to calculate how much is left over of the excess reactant. So let's first work on figuring out which one of these two is going to be my limiting reactant. I figure out how much product I'm going to make from 35 grams of nitrogen, and then how much product I'm going to make from 12.5 grams of hydrogen. Whichever gives me the smallest amount of ammonia, that is going to be the limiting reactant. So the first step for both of these is convert the grams to moles using nitrogen molar mass and hydrogen molar mass. 35 grams divided by 28.2 grams per mole. Grams will cancel, and I would get 35 times 1 divided by 28 and change giving me 1.249 moles of N2. I do the same thing for hydrogen. I start out with the amount that I'm given in the problem, 12.5 grams, times 1 mole of H2 weighs 2.02 grams. Grams cancel. 12.5 times 1 divided by 2.02, 6.188 moles of H2. So now that I have moles of both, I can use their molar coefficients here to convert from moles of nitrogen to moles of ammonia, or from moles of hydrogen to moles of ammonia. Here's my reaction again. And I have these amounts in moles that from the previous slide, just so we have them handy. And now I take the amount of moles of nitrogen and figure out how much ammonia I have. 1.249 moles of nitrogen multiplied by my moles of ammonia are on top and moles of nitrogen are at the bottom. And 2 moles of ammonia for every 1 mole of nitrogen, so 2 moles for 1 mole. These will cancel out, giving me moles of ammonia. And then to convert to grams, one more step, I multiply by the molar mass of ammonia, which is 17.03 grams NH3 for every mole. Moles will cancel out, giving me 42.5 grams NH3. Note that previously we've been breaking these up into 2 steps. In this one, they're all in 1 step. So this right here converts to moles of ammonia, and then this next step converts to grams of ammonia. I do the same thing with the hydrogen, so 6.188 moles times 2 moles of ammonia for every 3 moles of hydrogen, and then multiply once again with the molar mass of ammonia to get grams of ammonia. And note that the hydrogen gives me a larger amount of ammonia than does nitrogen, which means nitrogen is going to run out faster. Okay, I figured out how much product I make, 42.5 grams, and I also figured out which is going to be the limiting reactant, which is nitrogen. The second part of the problem asks me how much of my excess reactant is going to be left over. So how many grams of H2 remain? To figure that out, I take the moles of nitrogen that were given to me, or that I calculated, and then I figure out how many moles of hydrogen are needed to react with that exact amount of nitrogen. From the balanced chemical reaction, I know I have 3 moles of hydrogen for every 1 mole of nitrogen. 3 moles of hydrogen for every 1 mole of nitrogen. This moles of nitrogen cancel, leaving me with moles of hydrogen. Then, to figure out grams, I multiply by the molar mass of hydrogen, which is 2.02 grams per mole. Moles of hydrogen will also cancel, leaving me with 7.57 grams that are needed to react with all of the nitrogen. So out of those 10 grams that I had originally, 7.57 grams are going to react with all of the nitrogen. The nitrogen is going to run out, but 7.57 grams will be used up out of those 10 grams of hydrogen. Then the last step is going to be 12.5 grams of hydrogen, not 10. I was thinking of the previous problem, but 12.5 grams of hydrogen minus what reacted, this is going to be what's left over. So 4.9 grams of hydrogen will remain after all of nitrogen is used up. Here is a problem that it uses up the same, so it's very similar to the one we just did, uses up the same reaction, So calculate the mass of ammonia produced when you have 35 grams of nitrogen with 2.5 grams of hydrogen. How much ammonia are you going to make? One of these is going to run out faster. And figure out how much of the excess reactant is going to be left over when this reaction is complete. Just follow the previous problem that we just did exactly, and it will be just like it.